Right. Hey guys, so today we're gonna cover some of the core topics related to entanglement, and Jita is gonna talk
Yeah.
about
the actual implementation to use entanglement for communications.
So I'm gonna cover the first part of how entanglement works. So let's go. So we have an entangled state in quantum computing, which is one of the nicer states that we say, and the best versions of them are the Bell states. So we refer to them as the maximal quantum entanglement states. Going forward in the lecture, we're going to have quantum teleportation by Dittel, and then throughout the lecture, we'll be practicing using the IBM Quantum Composer.
This one, okay, yeah.
All right, so this is the link to the composer. So if you go to quantum.ibm.com/composer/files/new, you'd have to create an account to access the composer. And from there, we can go ahead and build some circuits. So I would recommend doing this first before I continue. And let me know when you're done. I'll just copy this link and drop it in the Discord. Do you guys have access to the Discord server, the ACM Discord? Okay. So I just sent the link there. I shall invite you to the server. Give me a second. But what's your email?
Maybe account for this.
Okay. So I'll continue later, but let's move on. So since you guys have access to the composer, let's start and understand and actually look back at some of the key gates that we covered in the previous workshop. So we have the X gate, which is the bit flip gate, more like the NOT gate in the classical world. But then we have the Hadamard gate, constructs sort of the superposition of states. We have the phase flip gate, the Z gate, and on the right, we have the basic quantum states. So the 0 state, the 1 state, superposition of the 0 and the 1. Then we have the psi state, which is a general representation of alpha 0 plus beta 1. And then we have the normalization, which is the condition that we always satisfy. And at the bottom, we have the C0 gate, which is the control knot. So if the first qubit is a 1, then the second qubit is flipped. So if the second qubit is a 0, it will be a 1, and vice versa, depending on the first qubit. So what exactly do we mean by quantum entanglement. So this state or this phenomena, it happens when two or more particles become connected so that they cannot be described independently, even when they're separated by very large distances. So think of it like some object A in this room can describe an object B or is somehow related to object B that is existing across the world, like 1,000 miles away or something, 10,000 miles away. So this is what we say that it is being entangled, as in they're both interconnected. And this is a good point. Like Einstein called this the spooky action at a distance, because measuring one particle instantly tells you about the other, no matter how far apart they are, which is kind of crazy to understand. If you cannot even see the state of the other object, how can you tell anything or state anything about it? So that is one of the key aspects of how quantum entanglement works. So moving on from this basic definition, I want to emphasize it a bit more. So in the classical world, we do have, let's say, two coins in separate boxes. If one is heads, the other is tails, they're always in that state, and the outcome is predetermined, but they're just hidden, so you can't see them because they're in the box. Like similar to having a red and blue sock in separate drawers. But in the quantum world, we have two entangled qubits. So let's say one qubit exists in this room and the other one is in China, and both are in superposition until they're measured. So that means that we don't know what state they'll be in until we actually go and open the box. So there are no predetermined values that exist, and measurement or the action of opening the box and looking at what states they're in, that creates both the results simultaneously. So that's how we know that if we open the box, we unbox the qubit here in this room and measure it, we're going to know what the other qubit looks like in China without even traveling to China and figuring it out. So yeah, just before we proceed, does this kind of confuse you, like what we're trying to say? Or is it makes sense kind of? Okay. All right. Moving away from like the abstract definitions, and this is the mathematical definition of entanglement, and a two qubit state being entangled, easier to understand in my opinion. So a two qubit state is entangled if it cannot be written as a product of individual qubit states. So when we say that we can write a state as a product of individual states, we say that it's separable, that is not entangled. So if you see the psi AB state, it can be written as a tensor product of the first state and the second state. However, okay, the example also shows you that. So the 0,0 state can be separated into ket0 tensor product ket0. But in an entangled state, this is one of the Bell states, it shows that there is no way of separating this term into a product, a tensor product term, like the above.
Yes. And I think last time we used the Jupyter notebook to actually prove the entangled state it cannot be separable. So if you have questions, you can just review that Jupyter notebook.
Yep. This is the important aspect. So if you look at a state and then you can figure out that, okay, like you can separate them into two qubit states, then it is not entangled. But in this case, like equation 7, it is truly entangled, and it is one of our main Bell states. Talking about Bell states, these are the maximally entangled two qubit states. And yeah, we're just focusing on two qubits right now. So as you can see in all of these states, there is no way of separating the two qubits, like into two separate qubits, the product of two separate qubits. And that is true for each and every one of them. And you can keep trying by hand or in the Jupyter notebook, but it has been proven that these are maximally entangled. And this question really emphasizes that. So what happens when you measure the first first qubit of the first Bell state? So looking at the Bell state again, we have the first equation 8, it says 1/√2 of ket 0, 0 plus ket 1, 1. So when you measure the first qubit, so let's focus on 0 and the 1. What do you expect to see, or what happens? So these are the options that we give you. So the second qubit will collapse to 0. The second qubit will collapse to 1. So there's a 50% chance that the second qubit is 0 and the 50% chance that it's 1. And the last option is that it depends on which result you get for the first qubit. So do you guys have any idea of how this would work? Because now you're trying to just focus and measure the first qubit of the state. So I'm gonna go back to the slide just to emphasize what the state we're looking at is, how it's represented. So we have 1/√2, 0, 0 plus 1/√2, 1, 1. And we're focusing on the first qubit. So what do you guys think? From these options, if you want to take a wild guess, what would you choose?
But in the first example, is the result already given?
Oh, sorry.
Yeah, it's D.
Exactly.
If your first qubit is measured to be ket 0, the second one will collapse to ket 0, 2. And if you measure and get ket 1, the second one will also collapse to ket 1.
Mhm.
That's
So
true.
it's not like the second one, there's only a chance that it would definitely be that.
Right, because we
Right.
see here, right? So we know that if the first qubit is 1, the second will always be 1 because that's our state of return.
Yeah,
So that means that it's entangled, right? If we measure this, we're gonna be left with 1 in the second qubit. If we measure the first as 0, we know that there is no other term that says that the second qubit is a 1. Like it's always 0 when the first one is 0. So that says that these two qubits are in an entangled state. One tells you the information of the other. Do you want to add anything?
no, I think that's good.
Okay. All good. Let's see. So yes, it is D, that it depends on which result you get for the first qubit. All right. So now we're gonna look at how we create these entangled states, and in particular, a Bell state. So we have with us two qubits in the state 0, 0. We start off by applying the Hadamard gate, which is our superposition gate. And following that, we apply the C0 gate. And here the C0 is conditioned on the first qubit. So when the first qubit is 1, only then the second qubit flips from its original state. So we apply H to the first qubit, then the C0, then we get the Bell state. And reviewing the math, similar to how we did it in the computer notebook, I believe it should be this. So in terms of the order, we have the H tensor I applied to the 0, 0 first. So this is how we write it. We write the operations on the right and the operations from right to left, depending on which ones are being applied first. And H is being written first because it is being applied to the first qubit. But for the second qubit, it is still the identity. So we apply H to 0 and we get 1/√2, 0 plus 1/√2, 1. And then it will be multiplied the Wheat tensor product with with ket 0 to get 0, 0 plus 1, 0. So this 0 just attaches to the intermediate state. And then once we have this, we apply the C0 gate, and according to the C0, it is conditioned on the first qubit. So it does nothing on 0, 0 because our first qubit is 0, but on the second state, it does flip the second qubit just because the first qubit was 1. And then we arrive at the Bell state, which is 1 over root 2, 0, 0 plus 1, 1. And again, this is perfectly entangled because we cannot describe these qubits independently. Yeah. With that, we're gonna try and build the Bell state in Composer, but before that, does anyone have any questions about the gates, what these are, and how we did this? I mean, does this make sense? Like the math? Because sometimes I get confused, like when I started looking at how these gates are applied, I used to think that why would H tensor I not be here and then the C not here just because we're applying this part first. But how I remembered it is that if this is our first operation, it has to be closest to the state it's being applied to, and that's how we keep progressing this way. So that is one thing that I would want to highlight. But does anyone have any questions about how we arrive at the first?
I missed the first part of it. So what does that H operate? Whatever the operation is like I?
Yeah. So I'll give you a brief overview of what we're trying to do. So we're trying to create this state, right? This is called the Bell state, and we're discussing entanglement. And entanglement means how describing one qubit describes the second qubit. So you cannot separate the two. And in terms of what's happening here, we're first applying the H gate to the first qubit, as you see here. But we're not doing anything to the second qubit. So how we represent it in the mathematical form is we have the Hadamard gate, tensor I gate. So since we're operating on a 2-qubit state, we need to have 2 operation gates. So identity does nothing to the second qubit, but the Hadamard is really applied to the first qubit. So once you apply the Hadamard to the first qubit, we're gonna arrive at just forget these 2 zeros. So we're gonna arrive at 1 over root 2 0 plus 1. And this 0 is tensored outside. And then it just multiplies and it just gets attached to the state. So the intermediate state when you do this product is 1 over root 2 0 0 plus 1 0. Does that make sense?
So just to be clear, the H
Yeah.
tensor, that one, it just turns the state into 2 possibilities, 0 0 and 1 0.
Right.
Usually
Right,
50%.
exactly. So that is the superposition gate.
Oh, and then the C naught just say, is it, C naught basically C naught something like if it's 1, then it flip the bits?
Right, so
Yeah,
the
so
C
like-
naught gate is a control NOT gate, so we have a control fixed on the first qubit. And since this is a solid circle, that means that if the first qubit is a 1, then only we apply, this is like the X gate, like it flips the second qubit just if the first qubit is a 1. But in this case, since we don't, like in this substate, we don't have the first qubit as a 1, it won't change it, so it remains the same. But in this case, since it is a 1, we're gonna get a 1 here. And that's how we arrive at the Bell state.
I think I remember someone saying like last week, it's like that's like tossing a coin when in midair and you change of one of the faces. It is still 50-50.
Exactly.
but
Yeah.
it's
Similar
out.
analogy. Yeah. Exactly. All right. So I hope the math makes sense. This is mainly to convince you that doing these operations actually help us arrive at the Bell state that we're gonna build in the composer.
And this circuit will be used to do the quantum teleportation circuit.
Yes. And before I continue, do you have access to the Discord?
Yes, I did. I verified myself as well.
Okay, that's good. So I dropped the link to the composer in the resources channel for you to access it. And
Yeah, I just saw it. Yep.
okay, you would want to create an account because we're gonna build the bell state in the composer. So this is the exercise that we're gonna do. So the state we looked at 1/√200 plus 1, we're gonna build it in the composer. So you should go to the IBM Composer, Quantum Composer website and create this circuit with 2 qubits and 2 classical bits. The classical bits are really used to store the measured values of the qubits. Having the qubits is of no value.
Right. So you can ignore that step right now.
And just go through these steps of adding a Hadamard gate to the first qubit and then the CNOT gate with the control on the first qubit and the action on the second qubit. And then we're going to add the measurement operations on both qubits to check our results. And yeah, the expected result should be that you should see only the 0, and 1 with roughly equal probabilities. And then we're gonna discuss these results, how we can infer entanglement. I'm gonna switch my windows to show you guys the composer. Let's see.
Why is it called a bell state? Is it anything to do with the bell state?
I'm not sure.
I think it should be named after a research.
The one who found the state, yeah. And that's how I assume. I mean, I never looked it up, but good question.
Is it working?
Yeah. Oops.
Do you want the background to be white so that it may be clear for the audience?
Yes, but I don't know how to go to light mode. But I'll try my best. 1 second. Oh, okay. Is this better?
Yeah, it looks better for me.
Okay. I mean, sure, it's slightly better. All right. Does everyone have has a composer working at least? Okay. Do you guys want to try building the circuit itself? And once you're done, just give a thumbs up so I know before implementing myself. So the steps were, we need 2 qubits and 2 classical bits. We're going to apply the Hadamard to the first qubit, that is Q0, and followed by a CNOT condition on the first qubit, action on the second qubit. And that should ideally give you the result. And you can work with the drag and drop circuit builder just for now. And you can see the Qiskit code on the right for you to review from last time on how you write Qiskit. Yeah. And you should see the probabilities on the bottom left. They should be equal or roughly equal.
This slide with instructions, or like splits.
Yeah, 1 second.
Remember, we only need 2 gates. The first one is the head, second one is CNOT, and that's all. After you add these 2 gates at the appropriate position, you can directly view the result on the lower left distribution chart.
C again.
Classical bits.
Oh, classical state with.
Yeah. So in our previous screen, we have C4, which means that we have defined 4 classical bits. But it's all shown in the same line.
Do we need 4 to this coverage?
No, actually, I don't think you need any one, any classical bit to build a distribution. Actually, if you do the measurement, it will actually destroy the distribution, whereas you know.
But if you do the measurement, it has to be stored in a classical bit.
Yes.
Mhm.
So if I do 2 measurements, let's say if I draw 2 measurements, and then I do this.
Yes. Or you can do some kind of overwriting depending on your requirements.
Yeah, in this case, we can have two classical bits to
Right.
separate the 2 measurements.
And your question actually answers partly why the quantum teleportation cannot achieve the faster than light computation.
So it cannot go faster than the
Speed of light.
Right.
Yeah.
Interesting.
Yeah, I will say later that people develop this kind of computation protocol basically because it's safe, because of its safety, not because of its speed. Yeah. And as you know, in many like the science fiction films, people will depict the quantum teleportation in some kind of very wild usage to transfer even like the physical particles from one place to the other. Not only information, but it's just fantasy.
But if you're not measuring it, then doesn't that mean that you can bypass that speed limit until you have to measure?
Yeah, but measurement is how we get information.
That is true.
Yeah.
Let's discuss at what 37, so 2 more minutes before I try to do it myself. It's been a while since I used the composer too, but it should be easy, sir.
And before I think you probably said we actually have shown 4 possible bell states, and this only implements one of them. So I think there's a later section. Well, after you guys get this basic bell state, you can add I think at least 1 more case to implement the other 3 gates, 3 bell states. Should be very easy if we have time for that.
Yeah. That would be more like an exercise to practice the composer and knowledge of the important gates we have.
So you mentioned like the speed location, which is interesting. So in the case of, I think, because I read something about breaking the RSA encryption. Theoretically, the whole in the Shor algorithm, there's a step where you have to guess you need to guess the numbers basically, but then what you do is you do a lot of exponential calculation.
Yes.
What the quantum Excel is doing that part, so they can calculate almost every single possible case. At least
Well, actually calculating like all kind of possible results at the same time, you do not need to study till sure to get this idea. I think actually the Deutsche Jews already have this idea, right?
Yeah.
Which will be taught next week, next workshop.
Yeah. To understand quantum advantage, I mean, Shor is the popular one because there's this big cloud that, oh, we're gonna have encryption broken in a few years when you have practical computers, quantum computers. But to understand where quantum advantage lies, we're gonna cover algorithms in the next couple of weeks to understand that. All right.
So we can continue.
Yeah, I'm gonna show you guys, and you guys can verify that you got the right result. Okay. So we do have Why are these many?
Yeah, you can click them, right? And then you can
Oh, what?
click on minus to reduce the number of classical bits in the gate.
Minus where?
You first you click on C6. Click minus.
Oh, wait. Why are there so many? Yeah, I need two.
Yeah.
All right. So we have 2 qubits and 2 classical bits. So first I'm gonna apply Hadamard gate. This creates the superposition. So as you can see, we have the intermediate state from the maths that we saw. So 0, 0, and 0, 1. This is written in there.
And
wrong.
also just notice the sequence.
Yeah, the endianness is flipped.
Right. And 0, 0, 1. So the 0 comes is actually the second bit here.
Mhm.
1 is the 12 bit. Just remember the sequence because later on we will use like a 3 qubits. May not be easy to observe just from the distribution of overlap.
Right. So the first qubit in the circuit diagram is actually the second qubit in the graph. So it's little endian. If that makes sense. Okay. So once you apply the Hadamard gate, I'm gonna just place our amazing C0 gate. So what it does is I'm gonna do it again. So here you saw that we have this. Let me refer to it as the 1-0 state because I want to be consistent with our slide. So we had the 1-0 state being flipped to the 1-1 state after we apply the C0, and that's what happens here. Because the first qubit is a 1, our C0 works and it just flips the second qubit, and then we get exactly the same probabilities. So we have our final Bell state of 1/√2 0, 0 plus 1/√2 1, 1. I'm gonna add the measurements as well.
Yeah, we will add measurement in actually destroy some kind of destroyed states.
Exactly. So once we have the measurements, you can see like the probabilities are.
Yeah, we will actually do the measurement, it will collapse to 1.
Yeah.
Right.
Exactly. So I hope this gave you an insight of how we can visualize our circuits and the graphs, as well as look at the sphere. We did cover the sphere last time, but the graphs and the circuit is really the important part. And on the right, it is useful to go over the Qiskit code as well. So after we have the necessary imports in the top, like Naren covered last week, we're gonna define our quantum registers, and we're gonna have 2 quantum registers. Similarly, we're gonna have 2 classical registers, and using those 2, we're gonna define the circuit on line 6, and this is our quantum circuit. Once we have that defined, we're gonna start applying our gates. So we apply the H gate on qubit 0 and apply the C0 gate, and here we have 2 arguments. So the first argument is the qubit on which C0 is conditioned, and the second qubit is our target qubit. So just to note, the C0 is represented using the CX because we're flipping the second qubit based on the first one. We also have the CZ gate, which is like a conditional C gate. So this is how we write the code in Qiskit. So after we have applied the gates, we do need to measure our qubits to get any values out of it. So this is how we do it. We do circuit.measure, measure the first qubit, and we store the measured value in the first classical bit / register. We do the same for the second qubit. So does that make sense to y'all? It should be pretty simple if you tried it on your own. If you fiddle around with this composer, it is actually very user friendly according to in my opinion. Yeah. So if there are no further questions, I'm gonna go back to our material. Let's see.
Is there any way to measure? Because it doesn't let me put the measurement first qubit after the second. Can only allow so Q0, I can only measure Q0.
That's some kind of like a cell compilation. Yeah, I think because functionally, I think they do the same thing, so it will automatically shift order for you.
Because you're measuring you, because I thought it was like, oh, if you measure 0, the first qubit, and it will affect the outcome of the second, since you're collapsing.
Yeah, but it makes sense in math, but from the circuit idea, we will just do the shifting order if you have two measurements, like
Back to back.
right back to back.
Good point. So with that, I mean, we just built the original circuit or the first bell state, but we do have 3 other bell states, and you can do this at home or take it as a challenge where the goal is to modify your current circuit to create each of the other 3 states as well. So I would recommend before using the composer and the try and test method, I would want you all to use a pen and paper, figure out what gates you have in your toolbox, and try to figure out how you apply the gates and to which qubits and in what sequence for you to arrive at these states. And remember that you have, let's say, like here we're given like add the Z gate to the second qubit, just because we're going from, if you remember, we're going from the +11 to -11, and we know that the Z gate is a phase flip gate. So this is an example of how you do it. And once you do the math yourself, you're going to be more convinced as to why these gates are being applied and how our state is changing. So I hope that helps. All right. Okay, I'm gonna hand it over to Tao to talk about quantum teleportation.
Right.
More interesting stuff. I was talking about the boring stuff. So
That's fine. I think the math background should be very important in this field.
Mhm.
Okay, you can stop sharing, right?
yes, you can just stop sharing.
Okay.
Yeah.
We'll pick up the remaining part. Okay, first. Sharing the screen. Okay, it works. We are at slide 13. Okay. Yeah, so we discussed a little bit about why quantum teleportation cannot be used for like a first than night communications. Partly because we have to do the measurement and use the measurement result to tell someone else at a distance far away. That channel cannot be implemented in quantum. That's the biggest limitations of that. But I can promise that this communication protocol is like a more secure than the traditional protocols.
You want to share your screen here to the Zoom as well, because it's recording.
Oh yeah. You can see it.
Yeah, looks good.
Okay, let us continue. So for example, we have 2 person. The first one is person A, Alice. The second one is person B, Bob. So if Alice has a qubit with a random state, we just simulate it to be alpha cat 0 plus beta cat 1. As you see, it's a very general state. The only limitation is that alpha square plus beta square should be equal to 1. That's the only limitation. We'll start with this general state, and we will prove that at the end of the protocol, Bob still has his own qubit with the same state as Alice's original qubit. And we also mentioned that this protocol is enabled by entanglement, that's for sure. And actually, Alice has one qubit, which is his general qubit. And the second qubit she has is one of the entangled qubit, so it's just one of two. And Bob has the one remaining entangled qubit. So in total, we have 3 qubits in this protocol. And here we show the exact step. First, we create an entanglement of that general qubit with the entangled qubit. So I can draw it here on the screen. So for instance, we have 3 qubits. And these last 2 is already in entanglement. For example, we have this state. And Alice will have access to the first 2. And Bob will have access to the last one. First, step 1, Alice will create entanglement using C0. So she will collect her qubit alpha cat 0 plus beta cat 1 with one of the entangled qubit. And later on, she further append hammer gate here. Here, after we append these 2 gates, I think it's interesting because it's just a symmetrical version of how you create the bypass state here. It's just symmetric circuit component. And after that, if you do the measurement of these 2 qubits, and the result of these 2 measurements will be sent to Bob. And Bob will use the result of these 2 measurements to do some kind of correction here. You can just imagine as some kind of controlled NOT, controlled Z gate. But as Bob may be very far away from Alice, we cannot just extend the control connection in the circuit to somewhere far away. And this card is usually done in classical communication channels. So that's the limitation of the speed. We need to send these 2 measurement results to Bob, well, the classical communication channel. Yeah, and finally, depending on the measurement result, we'll append X gate or Z gate. So if bit 0 and bit 2, which is like bit 2 get 0, 0, we actually like we don't activate the X and Z, just think it as some kind of control X and control Z. If we use solid control, these 2 are 0, 0, both control gates are not activated. So if it is 0, 1, because B2 is 1, we actually activate some kind of controlled X here. And if like both bits are 1, we activate both control. This shows the basic idea of how we use the measurement result to do the error correction. And as for why we need to do the error correction, we will show in the next part later on. So here's a more formal demonstration of the teleportation circuit. And yeah, you can take a picture here, and later on at the end of the tutorial, we will ask you guys to implement this teleportation circuit on Composer. As for the composer, I don't think the if-else statement to do the condition X and condition Z is not in, I think this feature is not implemented in the composer right now. So you can just replace with C0 and CZ gate in the composer. So you try to replicate this. So remember that we have this general state here. And we want to just kind of transport this state completely to Bob's qubit. And we have three, remember we have 3 qubits in total. So this first qubit state is shown here. And the second two is the Bell state. Because right now the first qubit and the remaining 2 qubits are not entangled, we can separate them with tensor product as shown here. And then we can combine them if you want. So first we have alpha cat 00 plus beta cat 11 tensor product with the Bell state. So this one leads to product with this whole stuff. So at first we will have alpha divided by square root of 2, and then we have 0, 0, 0 plus 0, 1, 1. And also remember that the beta state here also lead to product with the Intel state on the right. So similarly, we then have beta square root of 2, 1, 0, 0, because this one combined with this 0. Again, 1, 1, 1. Well, which is the same as what we can get in this expanded form. So that's the basic setup. We haven't applied any gate here. We just used some kind of expansion to get this one. Do you guys have any question?
In the case we have alpha 0 and then we multiply this to 1, 0, 0 right hand side, how does that lead to 1, 0, 0?
Where was 1, 0?
Like,
Oh, this.
Yeah.
This is not. These two are cancelled.
Oh.
No,
Okay.
so it's just 3 zeros here.
Okay. Yeah, I see. Okay. Oh, that makes sense.
Right. Yeah, remember we only have 3 qubits in this circuit. Okay, that's the basic setup. We do some kind of simplification to help our calculation steps later on. We haven't applied any gate here. And you remember that first gate in this protocol is the CNOT gate. It's shown here. It's CNOT from qubit 0 to qubit 1. So remember that controlled means that if the first qubit is measured to be 1, we activate the gate on the second qubit. So for all 4 possible states, we observe that this state has 1, the first qubit, and also this one. So we can just like copy this whole left part here, and then this is exactly what we get here. And to flip the qubits, we actually just like erase this 0 and this 1. So we get from 0 to 1, 1 to 0. And this is exactly what we get here. After CNOT, the remaining part of the entanglement here is the Hadamard gate. And remember that the Hadamard gate is also applied on qubit 0. So just a little recap, if we have Hadamard on cat 0, it will actually create 1 over square root of cat 0 plus cat 1, like a equal probability. And if we have Hadamard gate on cat 1, we actually have the same probability, but the phase is different. In this case, we have cat 0 minus cat 1. The probability of measuring these 2 possible outcomes are still the same, it's just a phase difference. With this simple rule in mind, we can apply the first qubit, apply the Hadamard gate on the first qubit. So if we have cat0 as the input and cat0 plus cat1 or cat0 minus cat1 as the output, so we actually have like two times the terms. So before we have 4 terms, and after that we have 8 terms. And the calculation is, I will just show 1 term to help you guys understand how we how at least how I use edge gate rules to help me calculate in a very simple way. So just take this term as examples. So its coefficient is beta over square root of 2. And 1, 1, 0. We apply the hammer gate on this qubit. So this one is splits into 1 over square root of cat0 minus cat1. And this is the only operation only on the first qubit, and the remaining 2 qubits are the same. So we just append overall coefficient here. And this qubit is tensor product with 1, 0. So if we simplify it, we will get beta over 2, 0, 1, 0, minus 1, 1, 0. This term and these 2 terms just corresponds to first this one and the second this one. For the remaining 3 terms, you do the very similar steps. And I can convince you that the final result you can get is this, like this whole expression with 8 terms. Okay, I should erase some of the notes. The final step is to do the measurement on the edit side. So I'll go back to the 5 steps. So step 5, we actually use the measurement of the first 2 qubits to depend on our following correction techniques. So for 2 kind of qubits, we will have 4 measurement probabilities. Actually, we can use these 4 possible outcomes to group our terms. So the first probability is 0, 0. The second one is 0, 1. And third one, 1, 0. The fourth one, 1, 1. From this step to this step, we only regroup the terms. We don't apply gates here. So these 2 expressions are essentially equal. We just do this kind of transformation to help you guys better understand the correction step later on. So from our final expression here, if we measure the first 2 qubits and we get cat 0, 0, what's the remaining part? The remaining part is alpha cat 0 plus beta cat 1. So the remaining part is on the 3rd qubit, the second entangled qubit, to be specific. And this is very, actually this is very special case because with our input, the qubit Alice want to send is alpha cat 0 plus beta cat 1. And if even we don't we just ignore the correction, we don't apply the correction in this case, the remaining qubit, the 3rd qubit is still alpha cat 0 and beta cat 1. And as our control gates suggest, because the measurement is still 0, control X and control Z is not activated here. So we don't mess our good result up. We still get alpha cat 0 plus beta cat 1 in the first case. The second case is 0, 1. If we measure 0, 1, the 3rd qubit will collapse to alpha cat 1 plus beta cat 0. And then remember that if we see there is a 1 on the 2nd qubit, we append X gate on the 3rd qubit. So after we apply the X gate on this gate, on the third qubit, we will have alpha cat 0 plus beta cat 1. The X gate is activated to transform this last qubit back to the information we want to send, as shown here. The third case, we measure 1, 0. The third qubit will collapse to state alpha cat 0 minus beta cat 1. And remember that our input should be alpha cat 0 plus beta cat 1. Remember how we describe how we can like add X gates and Z gates to implement the remaining 3 Bell states. And this is just one implementation that's very similar to implement other Bell states based on the cat 5, the 5 plus state we showed you here. So because we have like a -1, there is a gate called Z gate with input 0, it doesn't do anything. And if Z gate applies to cat 1, it will have a minus sign at the front. So this is exactly what we want. So we measure the first qubit and it is 1, we apply a Z gate, and after applying a Z gate, alpha cat 0 is still the same, because in this case, the third qubit, we can just think it as 0, and the Z gate, as shown here, applied on 0 is still 0, minus beta 1, we'll actually have a -1 here on this term. So alpha cat 0 is still the same, and minus beta cat 1, 2 minus will create a plus. So we go back to the alpha cat 0 plus beta cat 1. The last outcome is 1, 1. And in this case, we will activate the both controlled X and controlled Z on the third qubit. So in this case, our input is alpha cat 1 minus beta cat 0. We first apply the X gate. So alpha cat 1 will become alpha cat 0. And beta cat 0 will become beta cat 1. So that's the first step. The second step is that we apply a Z gate. I should use red pens to make it more clear. So Z gate on cat 0 is still cat 0. Z gate on cat 1 is minus cat 1. So first term is still alpha cat 0. The second term, beta cat 1 will become beta times -1 cat 1. So what we get is still alpha cat 0 plus beta cat 1. It's just simple proof of all possible measurement outcomes. And under all circumstances, the correction technique still works, so that the final state, at the final state of qubit 3, what you can get is the same as the input state. Is there any question?
Just to add, I mean, I don't know if you guys remember, but the Z gate is only adding the negative sign in front of the 1. So it only acts if the qubit value is 1. If it's 0, it doesn't do anything. And that is, I mean, the X gate always flips, but the Z gate is just a phase flip if the qubit is 1. Kind of conditional, but not really.
Yes. And as shown before, X gate and Z gate is also the only 2 gates you will need to transform the basic 5+ state to the other 3 Bell states. I think we can just skip the visual proof right now. It may be confusing. But if you have access to the slides later, actually append a link here so that you can play around with the block sphere. Yeah.
Yeah, we can add it to the Discord.
Right. Sure. So here we go. We have the teleportation circuit again. I think now it makes sense. So first we append a CNOT gate and then H gate, which is a symmetrical component compared with how we create a Bell state from cat 00. And later on we use the measurement result here. And these 2 classical bits are sent well traditional, like the classical communication channels is shown here. The double lines here means it's a classical channel. And based on the result, we will decide whether we want to append X gate there and Z gate here. But I think this kind of operation is not supported in IBM Quantum Composer right now. So you can just draw a control Z gate here and then a control Z gate here. So you can just use like normal CX and CZ gate on IBM Quantum Composer to show actually this protocol works. Okay, you can try to build this circuit again. Just remember that we have our Bell state ready by the start of this protocol. So you can continue your work based on your previous experiment.
So how much time?
5 minutes.
5 minutes. Okay. Yeah, let's try for 5 minutes and then here's how we can go over. How it's important. If you guys finish your review, just let us know.
Yeah, I will draw the whole circuit for you guys. The missing part is we have hammer gate and the CX gate to actually create the Bell state. If our input is 0, 0 here.
Do we have to draw those two? The one that you draw by hand? Do we have to put that on the?
I think that's your previous circuit, right? To create the Bell state.
Oh, the previous one.
Yeah, the previous one. We use that to create Bell state.
Oh,
Yeah, so if you haven't deleted your work, you can just continue your work on that one. Arch, can you try to draw the circuit? Oh, you already started. Yeah. H and two measurements. Yeah. CX and CZ. Mm. I think you need to use this stuff here. And Z, or you need to like drag Z first and then add. Yeah. And then this is easy. I've tried this one before, but you need to do it on the third qubit.
Oh, you're saying so.
Yeah, should be on qubit right.
But you're saying this is easy.
This is easy. If you click on the information, it shows it is easy. Yeah. And also you can always tell from the right hand side code. So you can shift back to the state vector. We have only 0, 0, 0 because our input is 0. The outcome we can get is always 0, and you can try to add H gate here. One more H gate on the first qubit. So the final outcome we can get is also these two, 0 and 1, with an equal probability.
Right.
Right. Yeah. I've tried to actually to draw the if statement here, but it doesn't work. So I can only use Control X and Control Z.
Yeah.
I think like 2 minutes later you can just share this screen.
Yeah.
Because I don't think there's any more notation I need to write down later on.
Yes. Yeah, that's fine. 30 seconds.
We're almost done.
Right.
A few more cents. Mm. You want to stop sharing?
Sure. Oh. Sure.
No. Right, so let's look at the There's a bit of lag. Yeah. So reviewing the circuit once again, we have the Bell state that we built earlier, but in this case we would have 3 different qubits, and the Bell state is formed using the second and the third qubit. And with that, we start off with applying the CNOT gate on the first qubit and the second qubit, followed by the Hadamard gate. Sorry, on the first qubit, Then we perform measurement on both the first and second qubit. And after, since we don't have this classical communication kind of operation in the composer, we're gonna straight up apply the CX gate, control the C0 gate, and how the circuit looks in the composer. So with our Bell state formed with the second and third qubit here, we apply the C0 gate condition on the first qubit and flipping the second qubit. Then we have the Hadamard gate here. And after that, we perform the measurement as shown in the previous diagram. And once we have the third qubit, and then we apply the CZ gate. So this is how the Z gate looks like. We use the, okay, I'm gonna do this again. So we use this conditional,
First the drag C.
the Z, yeah,
Yeah.
Z, I forget. Yeah, the Z and then the conditional on top of the Z, and it converts it to a CZ gate. You can click the info icon and it will tell you that,
Actually CZ gate.
yeah. What's it not?
This is lacking. Okay.
Oh yeah, on the left, right? You can see the CZ gate. And once you're done with the circuit, you can verify the code on the right. It should correspond to how the circuit looks. And on line 15, we have the CZ being applied, conditioned on the first qubit and action on the third qubit. Do you want to emphasize the state?
Yeah. So in this case, the initial the qubit state we want to set, which means the qubit state of the uppermost qubit is by default cat 0. So what we get after all this kind of operation is still 0, 0, 0 with probability 1. So if we add an X gate at the beginning, which means that originally the qubit we want to set is cat 1. So the final measurement outcome will also be 1, 0, 0, 0. And notice that the initial state, which means that the value of the qubit 1 is no longer 1. So the information is deleted once it is sent to the false qubit. And if we have like a little bit more sophisticated state, for instance, we have sorry,
How do you get that red line?
red line.
Oh, this.
Oh yeah, the
this
control
C-
Z.
Yeah, let me.
Okay.
So in the diagram, let me show the diagram again. So in the diagram, we have the control Z, right?
I think are you asking about how we do that in Composer, right?
Yeah,
Okay.
I was just showing what it was. So let me delete it. So you add the Z gate first
Right.
on the target, which is our third qubit. And then you add the dot, which is the control. So that specifies we're gonna have a control, but instead of dropping the control on the control qubit, which is a bit weird, that's how it should be. You drop it on top of the Z gate and it extends itself to the top, to the control qubit that we want. And once this is done, you can change what it is actually controlled on in the left panel. So right now we have Q0, which is our first qubit, but we could have Q1 as well. This is not the correct circuit, but I'm just trying to show how to change the control. And that goes for the target as well. So this is how you construct this easy gate.
Yeah. So in this case, the input, which means the qubit going to transport have an initial state of 1 divided by square root of 2 cat 0 plus cat 1, which means that initially the qubit will want to send
can be measured to be cat 0 with 50% probability and cat 1 to be 50% probability. And after all these kind of operations, in the end, the probability distribution is still 0 and 1 with the same 50% probability. So, well, this works for all kind of situations.
Yep, so just to take home the point, the first qubit was representing what Alice wants to send using the Bell state that we created in the second and third qubit. And after all this operation and the states, we get that after measurement, the third qubit is 0. This is the qubit that Bob got, and it should be 0 because that's what we started with. We started with 0 with Alice, and the other way that Detal mentioned was that if we flip the bit that Alice has, right? So if Alice started with a 1 and wants to send the 1 using the Bell state, Bob does get the 1 with 100% probability, telling us that this works.
And the initial one is permanently destroyed because we, as you see, there's only 1 out of these 3 qubits.
Right. Okay. So now we can continue.
Yeah, I think there's some facts we already discussed before because maybe use measurement outcome to help us the correction to transform some information classical channel. So that's the biggest limitation why we cannot achieve faster than light communication. And in these 2 classical bits to teleport 1 qubit of information as we shown here. There's 1 receiver qubit, 1 sender qubit, and we need 2 classical measurement outcomes to do the correction. Okay, let's go on.
Yeah, I can talk about this. So these are some other cool applications of what we discussed today. So quantum key distribution, it allows for secure communication with provable security. This is because our quantum states are very fragile to external noise. So we can implement these communication protocols using the quantum states. And this is indeed being used currently. Quantum computing, in terms of the advantage and power, entanglement is essential, and we're going to see that in a couple of the algorithms. So more entanglement means that the quantum computation is running in parallel systems, helping us compute faster. And the third one, quantum sensing, we do have ultra precise measurement and devices such as atomic clocks and gravitational wave detection devices that work on this technology. All right, to summarize what we learned today, we did cover entanglement at the start, which is a uniquely quantum phenomena where particles share a single quantum state, even at a distance. So you cannot describe a single qubit independently. Saying a thing about one qubit tells you everything about the other qubit. And that is what I would want you guys to take with you in terms of what entanglement really means. Then we looked at the Bell states, which are the maximally entangled 2 qubit states created with H plus C naught. That was the first Bell state. We do have the other 3 that use the X and the Z gates, and you guys can try it out to build them. Again, would recommend doing it by hand as well. Thirdly, Detal covered quantum teleportation, a very cool technique that guarantees how you can communicate the information between 2 participants using the Bell state.
Actually, that may be one of the technology that is already used in the commercial world.
Yeah.
So yeah, if you want to do something that is really related to the current use of quantum technology, it can be a good choice.
So this shows how entanglement is useful in a particular specific setting. And thus that brings home the point that entanglement is a critical resource for quantum advantage. And as I mentioned earlier, it will show up in a couple of quantum algorithms. So just a thought experiment. If entanglement allows for instant correlations, why can't we use it to send signals faster than light? And this is what Dital mentioned and with the discussion with you that we do need to measure classically in the process. All right, so for next time, we're gonna play a bit more with the composer, try to implement, we're gonna skip the super dense coding part, but we're gonna think about how entanglement could be useful in algorithms. So in the next coming weeks, algorithms and quantum advantage will be covered in depth. Then we're gonna have these two, which are the Deutsch-Jose and Grover search.
Yeah, and then in terms of complexity, these two algorithms have circuit which is well at the level similar to what we have, like at a like similar level to the quantum teleportation circuit.
Yeah.
So if you can understand like the circuit today, you can definitely understand how those circuits work in the following weeks.
And we leave you with some resources linked here. I'm gonna drop the slides in the channel and in the drive for you guys to access. But yeah, that's about it for today. Thank you for coming. Yeah.
Thank you.